Okay. Hello, everyone, and welcome to this ELISA Summit presentation. Let's have a quick introduction about us. I'm Alessandro Carminati, Senior Engineer at Radare, currently working in the Automotive Kernel Development Team.
Yeah, and I'm Maurizio Papini, Senior Software Engineer at Radare, and I'm working in the Functional Safety Team. Good morning, everyone.
This presentation is about generating static architecture diagram for specific kernel image. Next, please. Let's begin by having a 10 kilometers view of this presentation. We'll start by introducing the problem, then we'll detail the data extraction and usage phases, speak about the safety analysis relation, and at this point, we should be ready to see the demo of the tool we realized. Next step, we'll conclude this presentation. This work, as I said, is about generating static Linux software architecture description. The first argument here is that Linux kernel is a giant monolithic piece of software that has not a predefined subsystem decomposition. Components larger than function are not clearly defined. Safety analysis, on the other hand, needs software architecture description that highlights subsystem interaction, dependencies, and subsystem interface. In addition to this, ISO 26262 Part 6 requires a software architectural description specification that can be used to support safety analysis and drive test definition. The work we present here is about data gathering and processing to produce diagrams. Produce documentation on the software in general requires a lot of information on software under analysis. This documentation, if not available, the only option that remains is to recover this from the software itself. Let's see then which option we have. One option is to static analyze the source code. The alternative is to static analyze the kernel image binaries. Let's see pros and cons of the two approaches one by one. We'll start with the source code analysis. Among pros here, source code analysis is easier to perform by humans, since the code is written in high-level language. The analysis is not requiring any special tools. On the con side, we have the actual code executed derived from the source code, but the actual flows does not match it completely. During the compilation, in fact, the compiler can decide to inline function, which makes symbol disappear. In other cases, the compiler can choose to split function into multiples, and this produces new symbols. Other examples of modification introduced by the compilation are, for example, the introduction of implicits, like stack canary check. In addition, the source is usually preprocessed before the actual compilation. An example of this modification is the use of macros. As last comment, using source code, and the analyzer needs to figure out which code is actually used and which is not. Within a single C file, macros determines which code is compiled. But when you decide to consider a file or not, makes-file logics makes the difference. An analyzer that wants to take care of this aspect needs to analyze makes-files also. As last consideration, Linux kernel code is written in multiple languages. In addition to the standard C, architecture-dependent code is usually written in the assembly for that target architecture. And in future, Rust-based driver may also appear in the line. The other option is the analysis of the binary image. I can anticipate this one is the one of our choice. In the pro side, we have the binary image contains exactly what is run, and it is homogeneous, only machine language. Every optimization done by the toolchain is included and taken into the account during the analysis. In addition to this, if the bug information are included, reference to source code are also available, and we have everything we need. On the con side, we have handling binaries is difficult if performed by humans. Specific tools are needed to read binaries. And machine language verbosity makes difficult for humans to read and analyze the code. Because in our plan is not to make humans deal with the analysis, these cons listed here are not very relevant. Here is shown the tool's architecture. The data source appears in blue and includes the kernel configuration, the kernel binary image, and the maintainer's file. In red, we highlighted the external dependencies for this work, which are Radare 2, used for function names, cross-reference, and indirect calls, and the add2 line needed to associate each symbol to its source code file name. Finally, the yellow blocks, we present the tool components that we realized. The config extractor that recover binary metadata like version and configuration. The maintainers extract that produce the association between source code files and subsystem name. The collector that extracts data from image and places in the binary in the database. And the navigator component in charge for database, for reading the database and produce diagrams. Let's see into details how this data collection is done. Here is the function names and cross-references gathering. In an ELF packet binary, as the Linux kernel image is, the ELF header carries a lot of useful information. Symbol list is exporting using ELF header.symtab section. Function name extraction is then easy. It's just a matter of parse this table. Cross-references, on the other hand, are not directly reported by any ELF section. This means that in order to add them, the function body needs to be parsed one by one, looking for call instructions. The use of function pointer to implement a call is known as indirect calls. Detect and report indirect calls is generally a problem hard to solve. Indirect calls need to be used by driver inside the kernel, which result in countless indirect calls being distributed across the kernel code. Depending on the architecture, a function pointer call can be implemented using different specialized machine instructions that exist for any given architecture. Detect indirect calls is possible. Resolve this call statically is in general not always possible. The current tool implementation can guess a resolution only in a few cases. Uses of emulation tools like Killing, Unicorn, Anger, and Radare ESIL can help to resolve deterministic indirect call, but the other non-deterministic, like the example shown in the slide, cannot be solved. As you can see here in the slide, there is a vector of function, and the actual call is done by choosing one of them randomly. Summarizing, the tool reports only the presence of indirect call, but it is enough for our objective. Also, it makes the manual resolution simpler if needed. In the last slide, indirect calls detection was introduced. Albeit several ways to create indirect call exist, the most common method used by compilers is by using machine-specific call instruction. GCC and CLang used to compile the kernel source code make no exception. The Spectre vulnerability changed how indirect calls are handled in x86 target system too. Retpoline is the implementation technique currently used on x86 to execute securely indirect calls. We don't need to go into details of Retpoline implementation here. Still, it is essential to note that this target architecture, indirect calls cannot be identified just by looking at specific machine instruction. On x86, special symbols are defined for indirect calls through Retpoline. This fact changed indirect call machine language level by making them look exactly the same as regular call. To detect indirect call, the tool needs to look at this special symbol in addition to specific call instruction. Gathering file names. File names are essential for this work. They are needed to associate symbols to its subsystem. Binary images do not usually include the source file information unless the bug information option is enabled. When this option is enabled, source files are added to the ELF header as DORF additional section in the ELF header. Now we have reached the gathering of subsystem. Let's face a fact. There is no official definition of subsystem in the Linux kernel. Let's start by defining what a subsystem is in this context. The kernel community considers a subsystem as an entity within a maintainer's file. The maintainer's file is included in the kernel source code, and it is a simple text file formatted to be parsed easily. It contains various information about each subsystem it describes. Among the other things, the subsystem name, the list of the file belongs to it, are the essential information here. Looking at the maintainer's file, you can rapidly realize that subsystems defined through it can overlap on each other or even be completely include one another. There are cases in the maintainer's file where a single source file belongs up to 4 different subsystems. Looking at the graph shown here in the slide, subsystem representing the subsystem interdependencies, a single hub is evident. This hub represents the file system subsystem. Here you can see the famous Unix statement, everything is a file, being followed. Nevertheless, we decide to use the maintainer file suggested decomposition and use it to represent the kernel subsystem.
So the described process done by Alessandro showed what we use to analyze the kernel image, what are the steps to extract significant data. The analysis to be performed is a slow process though. So collect function names, cross-reference, source file names, and so on is a process that usually requires minutes to get done. So designing a tool that repeatedly goes through this process every time you query some information or you query to extract some information will reduce significantly the productivity of the tools. So it makes sense to collect the data once at all and to structure the data in a database. So moreover, having this information in a database allow us to decouple the step of collection from the step of extraction and data evaluation process. In addition to this, it allows data to be accessible easily through a standard and flexible interface and open up also possible third-party application integration. Here is shown the database schema that we use to collect and to store the data. We can see only a few entities over there. So we have the configuration, the configs, the instances, tags, files, and symbols. You can see in symbols a self-references, a self-relationship based on the fact that there is the caller-callee references. This simple schema can host multiple kernel image data and can store also kernel configuration and metadata useful for future references. After explaining the strategy of using binary kernel image as source data, is now the time to see one of the tools that make this statement possible. One of these tools, as shown in the previous architecture description done by Alessandro, is Radare 2. Radare 2 is essentially a reverse engineering tool. It is used to have a look inside the kernel image and reverse engineering it. It supports binary from several architectures and reduce the need of having different dependency for specific architecture. It provides out of the box a way to list all the function names, cross-reference, and query the reverse engineered component. And its design include also the way to interface Radare 2 with other software easily. So then the other third-party tools, as introduced before, is add to line. In fact, for our objective, combining the source code into a single binary has various benefits. But the file reference for a given symbol is needed to use the partition induced by the maintainer's file. This is because maintainer file define partition and subsystem on file base. Dwarf is the debug information containing files, symbols, and line association. This is the principal way this work is using to collect files information. Radare 2 is meant to set that support Dwarf, but it doesn't expose the way to use it. So that's why we choose to use another tool. Add2line is a bin tools, and it's meant to translate address into core dump, addresses from cron dump into source code references. Yeah, now let's have a look about some benefit for safety analysis regarding the data we are collecting here. Safety analysis, as said, require a software architecture description to perform various kind of analysis, various type of analysis, hazard analysis, fault analysis, highlight system interface and system dependencies. So usually a software architecture shall include a static view, so the system and to subsystem decomposition, the subsystem interface, but also a dynamic view related to functional chains, control flow, and concurrence of process. The work presented here today is about a tool that helps the kernel expert to build a static software architecture description. Moreover, working at functional level help also to extract functional chain dependencies. Finally, it's meant to say that data are collected directly from the version that will be run. And now it's time for a demo. So here you can see the outline. So at the first step, at the first general example, will show you the collector tool in action. And then we are going through few usage example of the navigator tool, the tool that is building up the graphical view of the results. And we are going to show you a call tree, a very huge call tree example, easily to extract from the kernel, showing dependency at functional level. Then we are going to have a look at how to simplify the call tree representation, working at subsystem level. And then we are going to view, if we have time, the use of the feature of not expansion, which allow to not expand some symbol or some leaves. Let's see the demo.
So today we present you the new version of the kernel symbol database. The newer version differs from the previous because it collects its data directly from binary image in place of source code. Collecting symbol from binary is allowing us to easily solve the multiple symbol problem, and it also allows us to symbols generated by the compilation process. This work is divided into repositories. The first repository is for collecting symbols, whereas the second is for navigate the symbols and producing nice call tree diagrams. While I was speaking, the first of the two applications was running, and we can see it did already a couple of steps toward the complete collection of the symbols. So we can see that it started by detecting the kernel version, which is the 6.0 RC2, and it collected also the config, which is useful to track down the kernel image that is collected, that has been collected. Here you can see also the analysis initialization and the Radare framework initialization. Worth noting that this video is not real time and the actual process is longer than we are seeing right now. Next, you need to collect symbols and file. For this, it would use the already initialized Radare framework, and it also uses Retpoline for files information. The last step you see here are the tags subsystem collection, which is done by using the maintainers file inside the kernel source. At this point, we can see the navigation. Here is configuration, database data, symbol at which start, and mode of operation. Now we can start looking at a sample run of the navigation tool. Here you see the dot produced, and looking backward, we can see the symbol at which it starts. Now it's time to display what has been produced and see the result of this, which should be a nice graph, or at least we hope it's nice. This is the graph. Let's make it wider. It seems to be not that easy to read, since there is a lot of symbols here. Let's navigate it. We can see a lot of symbols and a lot of arcs. But let's see if we can reach the beginning of this graph. Let's see, here, 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 here. We can see a lot of noise. This is the stack function here. This is the stack check. Each function needs to go there. Quite messy. And now we finally reached the begin, our target function here. Really complicated. It's not easy to see. And this is why we will need to make something here, because this function seems to be really complicated, the visualization. Let's see other part of this graph, but it seems, however, to be quite complicated. Still, it is accurate. Now, we found the both RCU that are called in this syscall. This is useful because we want to show you something to make this visualization easier. Now, let's see an overhaul of all the syscall. This is a script we compiled to evaluate the complexity of the syscall. And as we can see, syscall seems to be very complicated. They have a lot of arcs, I would say more than 3,000, and more than 1,000 nodes each, which is really complicated to visualize. Here, a complete list. Let's focus on the currently seen visualized function, which is the syscall getPid. Here the source code, and here you can see the implementation of the getPid, which is really tiny. As a matter of fact, it just calls a couple of times the RCU locking system, and then it just takes a value from the memory. So we should not expect that complexity. The complexity is evident that everything is all inside the locking system. Let's snapshot to the getPid function and let's see its data. Here it is. That simple function is about this, more than 100 nodes. So let's see if we can simplify its displaying in somehow. For example, we can remove the expansion of the RCU function. Here's how to do it. Now it seems to be less complicated, just 5 arcs and 4 nodes. It's now time to see another feature of this tool, which is the visualization of the subsystem interconnection. And here how to obtain it by changing its configuration. Let's run the tools with this new configuration and let's see the result, which we expect to be the subsystem interconnection. Here they are. And this is what they look like. Here the graph, we can see. Let's explore it a little. And let's focus on the start, which is here. That's it. Let's see a new run of the same tool, and let's simplify the visualization by removing the expansion of the RCU function. The graph we should obtain is should be less complicated than before. Here it is, just a couple of lines. And we can see less complicated than before. The last feature we want to show you is the simplification of the visualization when you are displaying the subsystem. For doing this, let's take another sample function, which is the send message. So let's see how this look like. Here it is, or the subsystem crossed during the function navigation. And let's use a feature to not expanding a symbol, a particular subsystem. Here we put the network subsystem here. All the networks, to be precise. But still, here the new visualization. Not expanding the networking subsystem produced that. That's all. Thank you for watching. So today we present you the new version of the
Okay, so well, some word about our next step for this work. We start designing a graphical tool to interact to generate a diagram dynamically, so that we can navigate expanding or not expanding some part. We want to automatically create documentation about subsystem interfaces, function used by other subsystems, subsystem dependency, to help the software architecture description. We want to also to refine the partition made by the maintainers in a way that we have to obtain partition with few non-overlapping subsystem and hopefully few subsystem. And then we want to highlight also global variables used by subsystem. This will help also to create dynamical view in the software architecture description. Then we want to start thinking about another step of decomposition from subsystem to software element. And obviously we want to push our code in the GitHub, in ELISA GitHub repository, and this will be done hopefully before this year, at the end of the year. Yeah. So this is it. I don't know if we have time to collect some questions. So there
are any questions. We have about 2 minutes.
Thank you. So I cannot see any question.
I will argue no question.
Okay, no, not a question, but a common integration with Elixir would be great. Yes, yeah, yes, would be great to have immediately, let's say, the link to the piece of source. Yes, thank you, Igor. Impressive. Yeah, the purpose, as said, is just to have a tool to understand and to verify relationship in the binary. So to highlight dependencies.
Another thing that our tools provide is produce documentation that help safety engineer to make their analysis. Because, as said, kernel is complex, is monolithic, and having a precise understanding on what interact with what is helpful when you perform a safe analysis.
Yeah, this is not going to remove expert judgment. So.
Thank you so much. And this session will end, and our next session will start in a second.
Okay. Thanks everyone.
Thank you, everyone.